Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you, organizers, and moreover, thank you people who are all keenly waiting for my talk. See, there are a lot of advantages for speaking at the end. So I have time till 1 o'clock. It's an open-ended talk. So I'll also guarantee that, I'll meet the expectation of the organizers. Organizers actually plan to do the damage recovery of all the equations that were bombarded on the first day by having no equation day on the last day. So I think I'll keep up the expectations of that. And I thank Manik for raising a lot of very relevant issues, and I think half the issues that I wanted to talk possibly Manik raised, but I am an academia, I don't worry about millions of images and millions of data points at this stage. So let me start with what people have been doing in computer vision for quite some time. So of course, given an image, we want to say this is a boat. And the problem is well posed or as a classification problem. So what people try to do is extract certain features out of this image and give it to a classifier, and the most popularly an SVM classifier, and it gives you the label as boat. And we all agree that, okay, this is what we all naturally would like the machine to do. And I'm sure this is what you will also do if I ask you to classify or label it. But if you look a little bit more carefully, I would like the labels to be a little bit more informative. I want the words boat, or there is a water. I possibly forgot on the first instance. There is sky, there is a hill, and the problem now gets naturally mapped into something which Manik discussed in detail, the multi-label classification. So is annotation a simple multi-label classification problem? It naturally gets formulated into this. So now let us look at a little bit more complex setting. So assume I am interested in this happening. 1 minute. Something went wrong. So assume I am interested in something like this. I want to go beyond the words and come up with a little bit more informative description of the image. That is, an ocean boat is traveling in a narrow water. The problem becomes a little bit more complex because I don't know whether we want to formulate this problem as where the output space is the number of possible sentences ever. And the associated challenges we all know, there are many. This is just putting some of them that were discussed in the previous talk. So we need to worry about correlation within labels. So is or within labels or within words present in the sentence. That is, we would like to know whether boat and water will co-occur and what is the probability of such co-occurrence. So all the correlation within labels. Weak labeling or missing labels is a very, very important and practical issue. That is the training data that you will get. So of course, so by the way, I possibly missed the point that we would like to formulate this problem as given a set of training data, we would like to generate algorithm which will do on a test data. So this is a problem setting. So if you want to talk about in the training data itself, the trees are missing. So when trees are missing in the training data, how do I label on the test data? And of course, the large number of possible labels, insufficient examples. So that is, I don't have enough examples to say that, to say what is a boat. So this is a still hard problem for computer vision researchers because they don't know what is the general description of a boat at this moment. There are a lot of variations in the images. And of course, if you look at this image, we all know it's a traveling. but it is very, very difficult to get that traveling word from a still image. I could have hoped that, okay, I will do better if I have a video where I can see it is moving and there is a word traveling can be attached to it. But from a one image, I want to get verbs. And so getting verbs from still images, and finally, like given these nouns and verbs, we would like to get sentences. So the problem is, we want to do something like this, and how do we do? And by the way, so this sentence that we had shown here is an output of our method. So if you look at the challenges from a machine learning or computer vision point of view, there are many. So first, if I want to know what's a boat, I would like to classify the pixels or the regions corresponding to the boat. So I would like to get regions, and then I would like to give it to a classifier. It says that it's a boat. So the question will come now, where are these windows or rectangles, and what size, what orientation, and that can immediately lead to millions of classification even in a simple like 1 megapixel image or 2 megapixel image that you have. It results in huge computational problem, and also you have on this axis you have problems like how many labels are there? Do you want these different classes or to share features somehow? Do you want some structured prediction models to do, and what are the semantics issues in category definition? So there are a lot of issues with that pops up in a machine learning and computational setting, and far more than that, we don't know how to describe the visual content. So these are all like we can hope of doing millions of classification if we know how to solve this problem. So the question now is that, okay, we are somehow not fully ready to solve this problem on one hand, that because I don't know really how to describe this visual content, and then there are a lot of issues which people are tagged, and there are a lot of progress has happened. So how do you connect these and still try to solve this problem? So this is the setting. So let me start with the work that we did a few years back, around 6 years back, on with a simple technique, how do you annotate or build descriptions. So this is a problem where we have a cricket video and we want to build a annotation of this. So if I want to look at process every frame or every clip or every shot and look at who are all there and what they do and come up with a description, it seems to be a very, very hard problem. So what we thought is we can do something else, that there's a look at something called a Cricinfo. There's a website which provides you the text information. So I have a video, I have a text description. So these two are in two different media, and they are completely like they are not going together. But if you can actually map these two into a different domain, so like for example, I can look at color of every frame and get a one-dimensional sequence. And similarly, I can convert the text into a one-dimensional sequence, assume. Then the problem is that of only aligning them. So I can do an alignment of text and video, and the moment I can align text and video, I can immediately get the descriptions for every shot. So every set of frames, I have now a clean description which is like actually a human annotated description. So the human annotated description is available for every shot, and with this shot, with this sort of an annotated description, we can look at building simple search engines where I can query specific words and get all the relevant shots or clips corresponding to that. Now, so this was the initial setting. So can we look at one more step, more complex processing? So this required only very, very minimal amount of image processing, very minimal amount of text processing to solve this problem. So can we go beyond that? So the next issue what we looked at is like, can we work with movies? So you have movies as videos, you have scripts as books. So I'm not talking about subtitles, I'm talking about scripts which come as books. So if you look at the books, the scripts, they have typically like a setting, like where some event take place, who are the actors present in every shot, and what they typically do, what are their expressions, what do they speak, all this information is available. To me, that's a sequence. Similarly, if you look at the video and do a little bit more complex video processing, I can talk about faces. If I use a speech recognition engine, I can get some text out of speech, and I can do a simple location recognition. I can get some information about indoor, outdoor, specific location information. Then the problem can actually be considered as, again, a sequence alignment problem. So here, if you look at how bad things can be, the speech recognition, a standard or a commercial state-of-the-art software, gives extremely poor performance on such a video, such a audio script. So we are not in a position to say that these individual recognition algorithms are very high performing and we want to solve the problem. But the clues available as few keywords in the speech or the audio is possibly good enough to say that which page or which paragraph of the script is actually matching with that shot. And this problem gets again formulated as a simple optimization problem with which gets solved with a dynamic programming. So with this background, we move to our more complex problem. Okay, so these are a couple of results where you can see there's a query word pics, and it gets retrieved from videos of where there is no audio present. Also, there is no issue. You can use the face and other clues to do that. So now the problem that we are interested in is a little bit more challenging. That is, you are given images and corresponding captions or sentences or annotations or descriptions, something like this. A cyclist relaxes on a bench and gazes towards the ocean. And given these images and descriptions, the challenge is now, given a new image, what is the description for the new image? So this seems to be not very obvious at this stage. How do we transfer, or how do we learn, and how do we transfer? So let us look at a simpler problem to start with. So we have a simpler problem now. What is the difference from the previous setting? So this time we don't have sentences, we have only words. So we have keywords. So you are given a new image, and we are interested in predicting the labels or annotations corresponding to this image. And how do we do that? We look at similar images. So the basic assumption is that similar images share common labels. So we look at similar images. How similar are they? Look at the annotations or the text attached to it, and we find a mechanism which will allow us to transfer these words to this. So basically, we want to propagate labels from similar images. So we want to look at the problem a little bit more carefully. So there have been like a lot of standard benchmarks which people use for various problems in vision, multimedia, and related areas. So we looked at one of the standard data sets which gets popularly used, Corel 5000 images for annotation, and a Pascal image which gets used very frequently for the classification. So one of the issues that I would like to take your attention at this moment is the labels per images. So a single image may have multiple objects. So if you look at the Pascal sort of a data set, it's mostly like one object is present, or one annotation is present, or at max like 2 or 3 or very few annotations are present per image. While if you look at Corel sort of an image which is popularly getting used, that has far more annotations or labels per image. So the popular data sets, I'm just comparing them here, which we are going to use later in the experimentation. So this is the Corel dataset, ESB games, IAPR, TC12 datasets, etc. They all have like a larger number of keywords per image or labels per image. So there are also standard train test splits which one can use for the evaluations. So if you, other issue that again came up was that if you look at the data, the number of labels or the frequency of the labels in the data set where it decreases exponentially. And if you look at the Corel data set, you see that the labels like water is present many times, but goat or sails is present only very few times. So these are the issues of the data sets. So before we try to solve this problem, we tag two issues which we find are possibly the causes of poor performance. Of course, one is this, the class imbalance, that is the frequency of labels vary a lot. The second is the weak labeling, what I called as weak labeling, where there are many obvious labels to a person, but they are not present. So in your training data, this image is annotated or could be annotated as boat, and the labels like water, sky, trees or hill or whatever it is, they are not being annotated because the person who created the training data thought that they are obvious label and there is no need to annotate it. So the problem is now so this can be used as a negative because these labels are not present here. So how do we address these two issues? So our solution is extremely simple. So we formulate this problem in a nearest neighbor setting. So the first step is where given an image or given a sample, we look at its neighbors and build a subset of it which is reasonably balanced. So instead of working with a full data set and looking for k nearest neighbors, we build a subset of it where, for example, there is at least one sample present with every label. So there may be, it's only at least, so there may be some of the labels may be present a little bit more than that, but it is approximately balanced. It's a very simple way of creating a simple balanced neighborhood to compute. And then you look at the new subset that you have formed, that is a TJ, and from this, from the new subset that you have bought. So if you can look at like something like this, you have a new subset, and from this, the samples in the new subset push the label to the test samples, and the push is proportional or inversely proportional to the distance of the sample with the template available or the training data measured in some feature space, in the image space. So what it does is something like this, that the water is not, though my nearest neighbor was that single image which didn't have the label water labeled, but I got some image with a water into my reasonably into the neighborhood, and then I look the image similarity, and that image pushes the water into my new image, new label. So yeah.
I'm a little bit confused. So this figure, right?
Yeah.
Circles, triangles, what are they?
So these are images, for example, with think of a simple one label at this moment. Think of a simple multi-class classification problem. These are all with one label, these are all with one other label, these are with another label, these are with another label. Let's think of simple multi-class setting. Their images, yeah. So now given a new image, you typically like find a k nearest neighbors, and in the k nearest neighbors, sometimes you may not get any of the far ones. So what we do is like make sure that okay, there is at least one image with every label present in the neighborhood, or some way of creating a subset which is approximately class balanced. It may not be fully balanced, but it is approximately balanced. But this cannot be used as such because still we need to look at the distances and neighborhood for actually pushing the label. So that pushing the label actually happens within this set, not in the full set. That's only difference. It's basically like you did so in a way we are also rejecting a lot of images in the first round and say that, okay, look, I have rejected a lot of things. I have a first criteria for screening and second a different criteria. Second criteria is what is we are more popularly using in machine learning, where we look at distances and push labels. Yeah, so it may be, so this is at this moment this is not a semi-supervised learning method. Yeah, so this is not a semi-supervised at this moment. So the issues of similar images share the same labels is also related to semi-supervised principles, what people say. Yes, that way it is related, but we are not formulating at this moment in a semi-supervised learning. It is. I'm not saying it is. So the supervised and semi-supervised, the principles remain the same. So since the key now is finding the distance function or using a distance function which can actually do this job. So we want to look at, like, can we do a little bit better with this distance function, and we go with a simple metric learning techniques. So the popular metric learning technique, the LMNN, what they do is given a neighborhood, we want to find a distance function such that your target neighbors come closer and your imposters move away from you. So you want to find a distance function which will do this trick, and that is done by optimizing an objective function which tries to put similar images or similar samples together and the ones which are far, far. So here if you look at, there are two terms, there is a eta and a y, which are basically 0, 1, where one says whether it, so the eta says whether it is in a neighborhood or not, the 0, 1 variable, and y says whether the labels are same or not. So there are two binary variables which plays some significant role in this formulation. So we thought of, like, no, this is mostly like defined for a single label classification framework. And our problem is more like a multi-label classification or an annotation setting. So what we do is we modify this a little bit, where instead of using a 0, 1 variable there, we have a variable push. And what is a how do you decide what is the variability of the push? It is based on how many labels you share between your between the images that you want. So this image and this image, how many labels you share, use that information to decide how much you want to push. So this push and pull are the words which people use in the context of LMNN, where you want to bring them close and push them far. So we modify this, and this naturally, and along with that, the distance also gets modified a little bit, because the distance or the comparison of two images are carried out with a variety of features, like starting from which some of them measure color, some of them measure texture, some of them measure something else. So all these features may have different properties and different preferred ways of comparison. Some of them may be happy with an L1 comparison, some of them may be happy with L2, some of them may be a intersection. So we have different ways of comparing. So we have a slightly different way of comparing these two, which comes with, so these are the number of categories of features, and within each category how many dimensions you have. So there are two variables which come W and V into the distance function. And that gets optimized in a very similar framework, but which doesn't get the full the analytical advantage of the LMNN. So we finally land up using a simple gradient descent based technique for solving the problem, with the constraint of sum of W is 1 and sum of V is 1. So these two constraints are making these problems a little bit more complex. So now we look at like how this method performs. So if you look at so these are the images. So we talked about the issue of imbalance in the labels. So we look at less frequent labels. So these are the less frequent labels, and these are the more frequent labels. This is for this data set, and similarly for all the three data set. And you can actually see the weighted KNN, which is the state of the art for these problems or on these data sets, is blue, where the new method is with a simple modification of the nearest neighbor, it improves the performance, and with the metric learning, it further improves it. And the interesting thing to note is that the method is not really towards the less frequent labels. It also works well on the more frequent labels. It is not deteriorating anywhere the performance on the most frequent labels, but on the more frequent labels, the improvement is not as significant as on the less frequent labels. That's all. Now, we have seen the issue of how do you annotate with a keyword. So given this, you can annotate as black, dog, and car, and given this image also, you can annotate black, dog, and car. But a black dog is sitting inside a car and a dog is sitting inside a black car are completely different. So the semantics that you get at this stage is possibly not enough for this problem. And now the question is, how do you go to the next level? So we extend the same ideas and move forward, where we start with for this sort of experimentation, we take these two data sets. One is a Pascal sentence data set, where for 1,000 images, 5 annotators have annotated the simple single sentences each. So you have 5 sentences for every image. And this is a little bit more complex and natural data set of 20,000 images with up to 5 sentences or a reasonably short paragraph description about it. So the question now is that, okay, how do you do exactly the same? So how do you do exactly the same with in this sort of a setting? So what we do is we use some simple text processing techniques to reduce these sentences into phrases. So now, given the test image and its neighbors with associated phrases, associated structured phrases I should say, because we know what is object, what is verb, what is attributes, etc. We know, we have tagged all this information. And so you have nearby images, and these nearby images propagate the labels to the test image. So the technique is practically the same, except that the annotations are no longer a set of only nouns or a set of keywords. It's a little bit more informative things. So this is used in pushing the attributes to the test image. Now, the process of sentence generation goes something like this. Given an image, we find the neighboring images with extracted phrases. So you have a set of images which are visually similar, which is measured in the image space or a feature space. And we also have the attributes or the labels or the phrases or a little bit more structured information from a text domain attached to this. And so these two are joined together, and from here we generate the full sentence. So this is how the input image is finally getting converted to an ocean boat is traveling in narrow water. So how do we do so the method is very, very similar. So when you do the phrase prediction here, similar to the labeling of propagating labels in the case of annotation. So here we do a little bit more strong language prior. So this language prior, which is popularly called the Google count, which says that, okay, how many times this sort of information or the phrase can actually co-occur, or phrase can actually occur in natural corpus, huge corpus. So this strong prior is used in computing the probability. So this is also similar to the standard way of the smoothing the probabilities in many of these cases where you may not have enough examples to compute the probabilities. So this allows you to predict the phrase relevance. And here also, when we do that, we tune the parameters in a setting where we want to make sure that, okay, visually similar images should share more labels, and this is sort of the notion of metric learning or the LMNN is used in a way to to find the better parameters, mu and w. These are the only parameters which gets tuned in this. So now, given this sort of a, so as a last step of this, so we have the phrases, and these phrases, from the phrases, we find the best combination. That is, we also know that, okay, these combinations can come together. So there's a boat, and then ocean boat is the one that should go together. Then boat travel and travel in water should go more together. So basically, we have a set of possible phrases of different types. That is object, attribute object, object verb, verb preposition object, etc. And from this combination, we select the best combination, more like a Viterbi sort of a setting, and gives you a set of phrases, and this is this is finally getting converted to a natural sentence. It's more like, this is called natural language generation, NLG. It's more like computer graphics, where you generate the sentence from the information or the structured information that is available here, and that gives you the sentence. So basically, if I conclude the process, there are two steps. One is we want to annotate with words and phrases. So when you annotate the words and phrases, we look at we talked about the weak labeling issue, and similarity of the images in the feature space is measured, and this is improved by finding an appropriate or a better distance measure. And in the case of phrase and sentences, there is some amount of role which comes from the computation linguistics, and we use the strong prior from the Google. And we also, I possibly missed discussing about the role of WordNet, which comes into the picture, where we find the synonyms and improve the descriptions. And this is implemented with many of the standard toolkits available in NLP. So these are few example image annotations. So these are an image, and these are the text which got annotated with these images. So this is another set of examples, results. Now, if you look at the annotations very carefully, so the weak labeling issue that we talked about, so this is an image. The method gave an output something like this, that is sky, buildings, window, roofs, and lighthouse. And if you look at the ground truth actually had overlap with sky and building. But window and roof, though it is present, is absent in the ground truth but depicted in the image. So the person who annotated thought that, okay, there is no need to annotate these things. So basically these are correct, but we can't measure it because the ground truth doesn't allow you to do that. And there are also incorrect annotations which comes as a lighthouse or something of that sort. So this is another example of weak labeling, where, so basically this says that many of the annotated words are actually relevant, though the ground truth is saying it is not relevant. So when you quantitatively measure, you will have to go with available ground truth. But if you clearly look, the performance or the words are actually more meaningful. So this says that, okay, there is a fly is possibly is incorrect. Plane, run, wing, road, they are all like absent in the ground truth. So these are examples of the sentence generation, where you have a image and it generates a sentence. A US fighter is sitting on a snowy tarmac, or a small sailor boat is passing near a yellow buoy, and an ocean boat is traveling in there. So there are two sentences we had shown here. One is with synonym and one is without synonym. So this synonym is where we talked about the role of WordNet comes in refining the phrases. This is another set of examples. This is another set of examples. A rail train is stopping at a small station. A rail train is pulling into a bus stop. So you don't possibly see the bus stop here, but looking at it, you may agree there's a bus stop somewhere. Yeah, maybe possibly you can see a bus stop here. So if you look at a qualitative comparison of this with some of the recent methods in related area, you can start seeing the difference, because many of them are actually based on a strong use of vision techniques. So basically they look for different familiar object detectors in the computer vision area. So they run such detectors and get tagged. So many of these people actually found a person in these images. So because the human detector may be giving a false fire at some place, and you also see the issues like person under the road, because the road may be present above the person in the image or something. So the phrases which may not have much meaning gets into the sentence that finally gets generated. So we avoid that because we use much more stronger language knowledge or the prior into the sentence generation. The another advantage of this is that, okay, you can actually, so as you had seen, we had multiple possibilities of generating the sentence at the last phase, and we took only the most probable one. So we should, if you have taken the second probable or third probable, you will get actually multiple descriptions of possible. So you can actually generate interesting multiple descriptions for every image. This is another advantage of it. And of course, you can also have simple human-like phrases which can be annotated for this. So there's a little bit more, this is in between the sentence and the keywords. So, and of course, we did quantitative comparison also on the standard benchmarks, where this is possibly the state-of-the-art tag prop algorithm, which does nearest neighbor and metric learning in some setting. So that gives you this sort of a performance, while our method is without metric learn itself is comparable or better than the state-of-the-art. So the sentence generation we try to evaluate in two different ways. One is with the help of human evaluation, where human says whether it is acceptable or good or okay or bad, and use the human evaluation to say that how good is it. So with synonym and without synonym we compared, and we found that this is the with synonym possibly performs better than the without synonym. And we also did a quantitative comparison with some of the previous work in sentence generation based on the measures like blue score, roach score, etc. Which are popular for machine translation and text summarization in community, and where we quantitatively we are superior than the previous methods. So what this doesn't say that we are anywhere near anything useful or immediately deployable system in sentence generation or high performance or high quality meaningful description generation. So there are lots of issues associated with in this area still left out. So for example, the models that we use are possibly very simple, but they are intuitive, and our motivation has been like we looked at the problem a little bit more carefully, and we found that okay, there are fundamental issues and many of them can be addressed with simple technique, but we feel that we may need that later stage as we move forward deeper and richer models to extend to possibly like annotation with lesser and noisy supervision, or explorations in scalability, as Manik has been worried about it, this issue of if you go to internet scale annotations, what are the other issues which crop up in this area. And of course, we also would like to use this text information that comes, can we actually use that back into the images in improving the understanding of the images. So the present trend is like people use the existing technique in image processing or image understanding, but like detectors or classifiers, you use back in text generation. So can you do the reverse, like at some stage can you use this information in improving the basic understanding of the images? That's all. I'll stop here.